Hey everyone, welcome back to Abstract Algebra. This will be lecture 15 of the course. And in this section, we are going to explore a concept similar to what we saw with factor groups, very similar, but pertaining to rings. So let's go ahead and jump into it. We'll call this section 3.3, Ideals and Factor Rings. Okay, so we saw previously how normal subgroups, this is a concept from maybe 6 lectures ago. Normal subgroups, we saw how normal subgroups allowed us to construct what were called factor groups. So normal subgroups allowed us to construct what were called factor groups. Okay, and it was a good lecture on that. We went through a bunch of examples, definitions, etc. And what we're going to talk about in this section is kind of the analogous concept for rings. So when it comes to rings, instead of normal subgroups, well, you've got some aspect of a normal subgroup, but you've also got the ring component, the multiplication component. And so what we have here are called ideals, and we'll define it in a moment. But ideals allow us to produce what are called factor rings. Okay, so it's going to be very similar in concept to what we saw before, and indeed a lot of the definition and the properties will overlap. But this is going to be a somewhat more complicated concept, this ideal and factor ring, because it's to do with rings rather than just groups. So a ring naturally has all of the components of a group, but also has the multiplication. All right, so let's go ahead and define an ideal. Okay, so a subring A of a ring R is called and we'll say two-sided. It's called a two-sided ideal of R if for every R in R, so for every element R in R, every element in the ring, and every A in the subring A, both RA and AR are in the subring. Okay, so very similar to what we saw with a normal subgroup, except now it's the concept expanded to a ring and a subring. Okay, so a subring is basically a subring A of a ring R is an ideal if A, the subring, absorbs every element of R. Right, so a subring A of a ring R is an ideal basically if it absorbs every element from R. And we use this term absorbs. Okay. So I mean, and to kind of put this into like more notation. So if basically R of A, what is this set? This is going to be the set of all elements R times A such that A is in A. Right, that needs to be a subset of A in order for RA to be an ideal. And since it's two-sided, you need this side as well, don't you? Okay. All right, so that's the idea of an ideal. Okay. So these are the ideals, right? This subset. Right, and we would say that an ideal is a proper ideal if, so A is a proper ideal of R if A is a proper subset of R. So obviously it can go both ways, right? Okay. All right, so before we see examples, I do want to throw out quickly a test for determining whether or not a subset is an ideal, and because we'll use the test on some of our examples. So I would just call this the ideal test. Okay, so a non-empty subset A of a ring R is an ideal of R if, now what do we have to test? Well, first thing we need is we need A to be a normal subgroup with respect to the addition operation, right? So we need A minus B to be an element of A whenever A and B are in A. And secondarily, we need RA and AR to be in A whenever A is in A and R is an element of the ring. Right? So we need these two conditions to hold in order for a subset to be an ideal. All right. Okay, so this one obviously checks the normal subgroup concept, and then this checks the multiplication concept. Let's see some examples. We'll start, of course, with the trivial ideal, right? And so basically for any ring R, you've got the additive identity and the ring itself are ideals of R. Now, those are both obviously the trivial cases, right? And we do call this one here we refer to as the trivial ideal. Let's take a look at an example that's less trivial. Okay, so what about this one? So for any positive integer, okay, the set nz. And what is this set? Well, this would be the multiples, right? So negative 3n, negative 2n, negative n, 0n, 2n, 3n, dot, 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 right? Both directions. This set nz is an ideal of the integers. All right, we can use the ideal test to confirm this, right? So to confirm, what would we do? Well, let's let n equal 2. Let n equal 2. So our subset here is A equal to 2z, right? And then what are those elements? Well, you probably know, but let's just be sure. Negative 4, negative 2, 0, 2, 4, and so on, right? So basically all of the even integers. And let's test it. So let's let A and B be in 2z. And we'll say, so since they're in 2z, they're multiples of 2, right? So we'll let A equal 2 times s and B equal 2 times t. Then we can test the additive side of this. A minus B, that's going to be 2 times s minus 2 times t, so 2 times s minus t. S minus t is surely an integer, right? And so that means this is definitely in 2z. Okay, so check, first condition. And then let's let R be in the integers somewhere. Okay. And let's let A again be in 2z, and we'll say A is equal to 2 times s. Then we need to check R times A. All right, so R times A is equal to R times 2 times s, right? And since these are just multiplication of integers, we know that that's equal to 2 times r times s. And so this is definitely in 2z. Okay, and then a times r is going to be the same thing, isn't it? So 2 times s times r, that's 2 times s times r, which is definitely in 2z. Right, so check. So 2z, right, this subset of the integers absorbs the integers, right? So this is an ideal. So 2z is an ideal of the integers. Perfect. Okie dokie. Let's see another example. Okay. So this is less of an example, a little bit more like a definition kind of, but let's talk this out. So let's let R be a commutative ring with unity. All right, so R is a commutative ring with unity, and let's let A be some element in the ring, right? Then the set, and we use this notation, we'll talk about that in a second, the set A given by R times A, such that R is an element of the ring, is an ideal of R. And it's actually a special kind of ideal. It's called the principal ideal. It's called the principal ideal generated by A. Right, so you can always do this for whatever A. You can do this operation, and you will generate an ideal in each case. Right, so this is basically just all of the elements of R that multiplied by the element A. Right, now it's important, this notation, you got to be a little bit careful. Notice that A is distinguished from the old notation. We used this previously to denote the set 0, A squared, A cubed, and so on. Right, so these are not the same. Just be careful of that. It's just notation. You just have the context matter, so you have to be a little bit careful. Okay, so that's another example. How about a polynomial example? How about an example from the polynomials? Let's let Rx denote the set of all polynomials with real coefficients. All polynomials with real coefficients. Okay, and then let's let A be the subset of Rx. All right, it's going to be the subset of Rx, and the subset specifically where the constant term is 0. Okay, so A would be equal to the set of polynomials in X. Well, I'm just going to write it out here. So this would be like A to the n, X to the n plus ... plus A1 X plus A0, such that A0 is equal to 0. Right, that's one way to draw it. Right, that's A. Right, so it's a subset of all these polynomials where this guy here specifically is 0. So turns out that A is an ideal of Rx. Okay, and I'm not going to prove it. I'll let you try to prove it, but I'll give you a sense for it. Let's just take a look at an example here. Let's just look at a couple of actual polynomials and see what happens. And I think, if we just kind of walk through an example, how you would go about proving this would be kind of obvious, right? So let's let A be an A, And let's define it. Let's just come up with an actual concrete example. So a of x we'll call, and we'll say that's 2x squared plus x. Now because it's in a, it's got to have a 0 constant term, so plus 0. And let's let r from r be r of x equals x plus 2. Now notice, in this case, this example is not in a, right, because the constant term is non-zero. Okay, so you've got an element from R and an element from A. And so if subset A is an ideal of this ring of polynomials, then it needs to absorb this particular example of R. And let's see what happens. Right, so I can start by multiplication. Let's do that piece first. So A of x times R of x. Well, that's just 2x squared plus x, and I'm not going to write plus 0 because it's not important. It's 0, right? And so when I expand this, you know what's going to happen. This is going to be 2x cubed plus 4x squared plus x squared plus 2x. Of course, that's equal to 2x cubed plus 5x squared plus 2x. And we can see that the the constant term is gone, right? Naturally, because it's going to get multiplied against a non-constant term, and so this is going to naturally be in a, right? And so this a is going to absorb everything from R, right? If you multiply a polynomial with a non-zero constant term against a polynomial with a 0 constant term, then the constant terms become 0 in the product, right? And so that would be like the multiplication side of the ideal test. Now let's say, for example, that B is another element of A, and let's let B of x equal, just any example here, 2x cubed plus x squared plus x, again plus 0 because B is in A. Then when I subtract B from A, what do I get? Well, I'm going to get the same kind of thing, right? I got 2x squared plus x minus this guy, 2x cubed plus x squared plus x, right? Now, obviously, there's no 0 term, no 0 constant term, non-zero constant term in either of these polynomials. And so there's not going to be one in the difference either. So I'm going to get 2x minus 2x cubed plus x squared, and everything else goes away. And so that's an element of A, right? So it's closed under that, right? And so you can see how this is going to be true in general for A and R, so defined. This is going to be true in general. So A is an ideal of Rx. Now this is obviously not a proof, but just shows you the example of how this thing works, and you can go about trying to prove it yourself. Okay. All right, so we've got this idea of what an ideal subring is. So now let's take this concept and let's explore the idea of a factor ring. Okay, so we're going to let R be a ring and let A be an ideal of R. Okay, so it's an ideal subring of R. Now, we know that R is a ring, so therefore R is a group under addition. So R is a group under addition, and that implies, therefore, obviously, that A is a normal subgroup of R. Right? An ideal is basically a normal subgroup that also has this property, extends this property to the ring side, to the multiplication side of the thing. Right? So we've got R is a group under addition and A is a normal subgroup of R. So we can form the factor group, right? So we can form a factor group of R, right? And we could say it's like, we could think of it like this: R minus A, and this would be R plus A, such that R is in R, right? So this is just the factor group concept from a couple lectures ago. So this part is clear, right? An ideal is definitely has a normal subgroup properties, and so given that and the fact that R is also a group means we can form a factor group, right? So how can we form a ring of this group of cosets, right? So if we've got these cosets, so given these cosets, how can we form a ring, right? So what can we do? How can we form a ring of these cosets? So the addition part we'll just assume is taken care of, right? The addition part is taken care of. What about multiplication, though? Okay. So kind of by analogy, we can develop the multiplication side of this. So we can define the product. Okay. The product of two cosets. Okay. And we'll say S plus A and T plus A. Is, right, so we'll just write it, S plus A times T plus A is equal to ST plus A. Okay. Okay, and so this is the multiplication of two cosets. This is the operation that we use for multiplying two cosets. Right, now remember when we added, right, we said that that was S plus T plus A, right, like this. Right, and so here's the multiplication that goes with that. Now this definition of, multiplying two cosets, the product of two cosets, this definition works as long as A is an ideal. This works as long as A is an ideal. Now, if A is not an ideal, then this does not work, right? And so, just like you can't talk about factor groups without normal subgroups, you can't talk about factor rings without an ideal. Okay, so let's see the theorem. Okay, so the theorem says let's let R be a ring, and let's let A be a subring of R, of course. Then the set of cosets, and I'll just write it like this, R plus A, such that R is in R. Okay, the set of cosets is a ring under the operations. Okay, so you've got your addition, S plus A plus T plus A equals S plus T plus A. And now you've got the product too. S plus A times T plus A equals ST plus A. Okay. Now, this is true if and only if A is an ideal of R. Okay, so you need A to be an ideal subring of the ring R. Okay, all right. Okay. All right, so we're going to prove this. We're going to walk through a proof of this just to kind of get a sense for why this works. Right, but this is the big theorem here, right? So you've got basically analogous to the concept of a factor group, but with rings. Okay, so let R be a ring and let A be a subring of R. Then you've got a set of cosets, R plus A, such that R is an R. That set of cosets is going to be a ring under these operations, and that's true if and only if A happens to be an ideal. It's a special kind of subring. Okay, so let's go ahead and prove that. Let's write a proof of this one quick. All right, so what do we know here? We know already that the set of cosets form a group under addition. So we know that part. We'll say we know that part from the group theory side of it. We know that the set of cosets forms a group under addition. Okay, so we've got that piece. So once we show that multiplication, so defined, is indeed a binary operation on the cosets, then we'll need only show that that binary operation is associative and distributive over addition, right? So we need to show that multiplication is a binary operation on the cosets, right? So once we show that, then we need only show that it is associative and distributive. Okay, right, so basically, therefore, what do we need to show? Basically, given all of this, what we really need to show is that S plus A times T plus A equals ST plus A is well defined. We need to show that it's well defined if and only if, right, i.e. it's going to fall short. It's well defined if and only if A is an ideal of R. Right, so it's the if and only if statement can really be reduced to this, right? So if the thing is well defined, then A is an ideal. And if A is an ideal, then this operation is well defined. Okay? So let's take it, let's do both directions here. So we'll start with this. We'll assume A is an ideal. And let S plus A equal some other element in A, S prime plus A. And then also we'll need another one, so T plus A, we'll let that equal T prime plus A. Okay. Now what we need to show is that if this is true, then ST plus A will have to be equal to S prime T prime plus A, right? That would follow, right? If S plus A is equal to S prime plus A and T plus A is equal to T prime plus A, then when I multiply, I need to retain that fact. Okay? And so this is fairly easy to do, actually. So by definition, we know that S is equal to S prime plus A and T is equal to T prime plus A. Right, and so here, oh, I'm sorry, I wrote that wrong. So S is equal to S prime plus little a, it's an element, and T is equal to T prime plus little a. And in this case, A is in, oh, darn it, I mean to make that a B, sorry about that. A and B are elements of A, okay? Okay, right, so this is just by definition. And so what happens when we multiply S and T together? Right, that's going to be S prime plus A and T prime plus B. And so what do I get? S prime T prime plus A T prime plus S prime B plus AB. Now, that's next, right? That implies that st plus a will be equal to this whole thing that we just multiplied together plus a as well, right? Now, what's going to happen here? What's going to happen with this expression? So this thing here is going to be in a, right? Because a is in a. And this thing here is going to be in a because b is in a. And this thing's obviously in a because they're both in a, right? So these are all going to get absorbed. Right? And so this whole thing is just s prime t prime plus a. Okay. Right? And so there you have it. So you've got this is equal to that. So st plus a equals s prime t prime plus a. Right? And given that, that means, what does that mean? That means the multiplication is well defined. Right? And obviously that's all dependent upon the fact that this works and this works and this works and a is an ideal. Right? So when a is an ideal, you get this operation working. Right? So let's look at the other direction now. Okay? Right? So what have we shown? We've assumed that if a is an ideal, then this multiplication operation is well defined. It has all the properties we need. And so let's look at it from the other direction. So here what we need to show is that if a is an ideal, then you've got this multiplication operation working. Right? So let's assume that a is a subring. A is a subring of R. So assume that a is a subring of R that is not an ideal of R. Okay. All right, so we're going to think about the reverse. Right, so then if that's true, then there exists an A in A, and there exists an R in R, such that A times R is not in A, or R times A is not in A. Right, one of those is true, right? The fact that A is not an ideal means that one of these products isn't going to work for some A or R. All right, so just for convenience, let's just say we'll just say that A times R is not in the subring A. Okay, so then let's consider the elements. Consider the elements A plus A equals 0 plus A. Okay, and then separately R plus A. Okay, so these are cosets, right? Well, let's see what happens when we multiply here. So clearly, A plus A times R plus A is equal to A times R plus A. That's fine. That's fine. But what happens when we use the other way to express this? 0 plus A times R plus A. Well, that's 0 times R plus A, which is just equal to A, right? The whole thing. So you're outside of the coset. Okay. And so in this case, AR plus A is not equal to A. And so in this case, the multiplication is not necessarily well defined, right? Because we don't have an ideal. So the multiplication is not well defined. Okay, right? And in that case, obviously, the set of cosets is not a ring. Okay, and so that's the proof, right? A little speedy, right? But that's the basic idea. Go back through that and make sure that all of that makes sense. Okay, let's see some examples of factor rings. Okay, so we've defined it, and let's take a look at some examples. So here's a good one, a nice intuitive one. So if I take the integers mod 4z, okay, so what is that? Well, it's going to be 0 plus 4z. It's going to be 1 plus 4z, 2 plus 4z, and 3 plus 4z. Now, what are these cosets? Right, just to make sure that this is crystal clear, what are these cosets? 0 plus 4z. Well, that's going to be the set, and I'm just talking about the positive side. The negative side will be here as well, but 0, 4, 8, 12, 16, and so on, right? What's 1 plus 4z? Well, that's one more than each of these. So you've got 1, 5, 9, 13, 17. 2 plus 4z. That's equal to 2, 6, 10, 14, 18. And 3 plus 4z. Right, that's going to be 3, 7, 11, 15, 19. All right, so that's obviously everybody, right? And again, I'm just looking at the positive side. This would also extend in the opposite direction as well, so I should put these dots here. Okay, so that would be, you'd also have the negatives in there. Okay, and so how does the addition operation work here? Let's take an example. So if I have 2 plus 4z, for example, that coset plus this other coset, 3 plus 4z, right? Well, I know that that's just the addition of the front two, so it'd be 5 plus 4z, right? But 5 is really 1 plus 4 plus 4z, right? And so that's really just 1 plus 4z, right? And so basically what this is saying is if I take something out of this coset and I add to it something from this coset, I end up in this coset, right? So for example, if I take 6 and 15, so 6 is here and 15 is down here. 6 is in this one, 15 is in this one. If I add those together, what do I get? Well, I get 21. Now where's 21 going to be? Well, 21 is up here. 17, 18, 19, 20, 21, right? So it'd be the next one, right? So it's in 1 plus 4z, right? So this coset plus that coset equals that coset, and all the elements in there would follow that law, that principle. What about with multiplication? If I multiply these same two cosets, 2 plus 4z times 3 plus 4z, well, what I should be able to do then is multiply the front two here, and I get 6 plus 4z. Well, same as before, this is really 2 plus 4 plus 4z. And so 2 plus 4z is really the key here. And so what that means is elements from, when I multiply things in this coset, i.e. here, against things in this coset, I end up in this one, right? So I can take an example, so if I take 2 out of here and 7 out of here, so 2 times 7, that's 14, and so 14 is back in here. So this one came out of here, that one came out of there, and the result ends up back in 2 plus 4z. And that's true in general, right? And so this is a great example. This is a ring. This shows how you've got a ring with these cosets. Okay. How about another one kind of similar to this, a little bit more more complicated and also simpler in some sense, right? So what about this factor ring? 2z mod 6z. Okay, I think I'm saying that backwards. 6z mod 2z. No, 2z mod 6z. Yeah. So what are these cosets? You've got 0 plus 6z, and you've got 2 plus 6z, and you've got 4 plus 6z. Are there any others? Nope. these are them. Let's see, what are these? Let's actually write these out, at least the positive side. So 0 plus 6z, that coset, what are the elements? So you've got 0, well, you got dot, 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 0, 6, 12, 18, 24, and so on. 2 plus 6z. So there you've got 2, so 2 more than this, and then 8, then 14, 20, 26, and so on. And then 4 plus 6z, right? That's going to be your 4 and 10, 18, 24, 30, 28, sorry. Okay. Right, and so everything is here. All of the evens are here. You take 2z and you mod it out. So, and you get 0, 2, 4, 6, 8, 10, 12, 14, 16, 18. So everything is captured here, right? Right, and again, the addition, right, how would it work? So if I take 4 plus 6z, the coset 4 plus 6z, and I add 4 plus 6z to it, maybe add it to itself, then I get 8 plus 6z, which is 2 plus 6 plus 6z, so really just 2 plus 6z, isn't it? And if I multiply, then I get 16 plus 6z, right? And so this would be like 4 plus 12. And the 12 would get absorbed by the 6z. So this is 4 plus 6z. Okay. So it's really modulo 6 that we're interested in here. All right, and so that's another example. Okay, very good. And there's lots and lots of other examples that you can look at. The integers are, well, you can imagine there's probably infinitely many interesting examples to look at. So one last definition. Okay, one last definition, and then a nice example. So a prime ideal. A prime ideal A of a commutative ring R is a proper ideal of R such that AB, two elements in the ring, right? If I take two elements in the ring and their product is in the ideal, right? So if I take any two elements in the ring and I find that their product is in the ideal, then that's going to imply that A is in the ideal or B is in the ideal, right? That's what we mean by a prime ideal. So a prime ideal A of a commutative ring R is a proper ideal of R such that for any A, B, and R where the product is in A, the implication is that A or B are in A, right? Part of the ideal. Okay, so that's the prime ideal. Right, and so the only ideal that properly contain, okay, and then, well, there's a second. Hold on. Let me make sure I get the second part of the definition also. So there's a second part of this definition, and that is the idea of a maximum ideal. A maximum ideal, A of R, is a prime ideal. No, sorry. A maximum ideal A of R is a proper ideal of R if whenever B is an ideal of R, whenever B is an ideal of R, with A a subset of B being a subset of R, then B is equal to A or B is equal to R, right? So the only ideal that properly contains a maximal ideal, like the largest ideal you can have, would be the entire ring. Okay. Right? So that's the idea behind a maximal ideal. So as you can imagine, there are different sizes of ideals. All this is saying is there are different sizes of ideals, and there's one that's the largest, right? And that's what we call the maximum ideal, right? So we saw that, 0, for example, is an ideal, and we see that the ring itself is an ideal. Now in between there, you're going to have different ideals, and one of them is going to be the maximal, right, in size. Okay. So that's the idea of the maximal ideal. Now the prime ideal, right, these are just two special ideals that exist, right? The prime ideal, now that the motivation for the prime ideal comes from the integer. So let's take a look at a kind of crucial example here. The prime ideal is motivated by the example coming from the integers. Right, what example? Let's talk through the example. All right, so let's let n be an integer, and let's let n be greater than 1. Okay. Then in the ring of integers, right, in the ring of integers, the ideal, we saw earlier that nz is an ideal, right, every time. The ideal nz is prime, well, is a prime ideal if and only if n is prime. Okay. Right, so I mean, the definition of a prime ideal doesn't say anything about prime numbers, but the motivation for the concept of a prime ideal comes from this example of prime numbers in the integers. Okay, remember the prime ideal says a prime ideal A of a commutative ring R is a proper ideal of R, such that where it's a proper ideal of R where for all A, B, and R, if the product is in the ideal, then A or B is in the ideal. Okay. All right. But in reality, this concept comes from this example, right, where we've got n and z. We know that n times z is an ideal. Well, it turns out that n times z is a prime ideal if and only if n is prime. So let's see why that's true. Okay, so we'll start, we'll go this way first. So let's let nz be a prime ideal. We'll let nz be a prime ideal of z, the integers. Okay, and we wish to show that n is prime. Can we do this? Yes, we can do this, right? So we're assuming that nz is a prime ideal, and we wish to show that n is prime. So what we're going to do is we're going to assume the reverse. Let's assume n is not prime. Okay, right, so if n is not prime, it's obviously composite. So let's let n equal st, where s and t, where 1 is strictly less than s, which is less than n, and 1 is less than t, which is less than n, right? So that's the definition of a composite. Okay, and so, right, so if n is in nz, right, then st is in nz, right? But also, of course, s and t are they're integers, aren't they? Yeah. Right. So since nz is prime ideal, by definition, s is in nz or t is in nz. But this is not possible. Right? This is not possible since what? 1 is less than t, which is less than n, and 1 is less than s, which is less than n. What is nz, though? Right? nz is equal to 0 plus or minus n, plus or minus 2n, plus or minus 3n. Right? So if s and t are supposed to be in nz, where are they? They can't be, right? Because they're somewhere between these two successive entries. Right? So you've got a contradiction. Right? So that means n must be prime. Okay? Now, what about the converse? Let's do the reverse. Let me flip my page here. Get one more. Okay, what about the converse? So conversely, let's let n be prime. Let's let n be prime. And we wish to show that nz is a prime ideal. Okay. So let's let a and b be in z, and the product ab be in nz. And we wish to show, what do we wish to show here? We wish to show that a is in nz or b is in nz. Okay, well, we know that n divides ab, right? Right? If ab is in nz, then n must divide ab. And since n is prime, n divides a or n divides b. This is Euclid's lemma. Okay, so that implies that a is equal to nk1 or b is equal to nk2. Right? K1, K2 are integers, right? Well, then that's it, right? That means a is in nz. That's this one. Or b is in nz. We don't know which, but one of them's got to be there, right? Right? And so the implication, right? So if a, b are in z and the product is in nz, and if that together implies that a or b is in nz, then nz is a prime ideal. All right, and so that's that. That was just an example, wasn't it? Well, that's a proof of the example. All right, well, I think we'll stop there with this one. Right? And now next time we'll get into ring homomorphisms. Right, similar to the idea from group theory, group homomorphisms, but this will be for rings, obviously. Right, and I think we're nearing the end of this of the course. Only a couple more lectures left, and they'll all be on special kinds of rings after this. We'll talk about ring homomorphisms, and then we'll get into polynomial rings and different items related to particular types of rings. Okay. All right, we'll end it there, and we'll talk to you all next time. Take care.